Okay. Hello, everyone, and good afternoon. Welcome to ECE 350. My name is Professor Sayed Majid Zahiri, and I'm going to be your instructor for this course, this term. Now, before I get started, I want to say that the lectures are being recorded. So after this lecture, you can use the same link to watch the videos. The other thing to note is that your questions that you would post on the Q&A will also be recorded. So if you don't feel comfortable for your questions to be shown to others, you can definitely just use normal emails to ask questions. Yeah, so gonna go ahead and get started. First of all, can someone, before I get it started, in the Q&A, post a note you guys hear me and see me? Great. Okay. So one thing to note is that you're getting my voice and the video with a 20 seconds delay. So bear with me with that one. Okay. So let's get started. Today we're going to see how things work in ECE 350, and once that's done, we're going to see. Give me a second. Okay, sorry. So we're going to see, we're going to start talking about operating system, what they are. And then at the end, we're going to talk about what makes operating systems exciting. Okay. So as I mentioned, the lectures will be online. We're going to present them on Microsoft Teams. We're going to provide the link before each lecture, and the recordings will be available afterwards. Office hours are also going to be on Teams and online. And then lab tutorials will be posted and delivered asynchronously. So your lab instructor will record videos and then present it to you. Who are we? So as I said, I'm Professor Sayed Majid Zahiri. I work on the intersection of computer systems and algorithmic game theory and theoretical computer science. I've done a lot of work on data center management, resource management, So that's my field. Your lab instructor is Irene, who will deliver the labs. You have three TAs. You can see their office hours. You can see their emails. They're going to be helping you with the labs. I'm going to keep an eye on Q&A as well. I got a bunch of these. I'm going to publish all. Okay. Now, 3 useful links. First is the course website. Everything from the lectures are going to be posted on the website. Also announcements. I'm going to use Learn, the course website, and probably Piazza to post announcements. So here is the link. You can actually download right now the slides. Let's actually look at the website. ECE 350. Let me share the. So here's your website. You can see your TAs, me, myself, Irene, the textbooks. Here is where the announcements will be posted. Here is a tentative schedule. You have all the weeks going all the way to the end of the semester. There would be no classes, obviously, in the reading week. All the deadlines for your projects are being listed here. Once we start with quizzes, the deadlines for quizzes will also be listed here. So in this column, I'm going to post lectures and then how long each one of them will take, identified by the colors. You're going to get the readings. So this is OSPP basically is your textbook. And then this is chapter 1, for instance, or chapter 2 or whatever that comes afterwards. These are resources that you can use for the quizzes because we don't have exam. I'll talk about that. And then here are some questions and answers about the course. Definitely take a look about quizzes, about the lab project, and all of that. So hopefully everything is clear there. Now let me go back to the slides. Okay. Great. The second link is Piazza. Use that link definitely to ask questions, anything about the lectures, anything about the lab. And then the last one is an anonymous feedback form. I actually would appreciate if you guys, I got course website too. So somebody's asking about Teams links being posted on the website. Well, unfortunately not. Well, maybe I can. I'll think about it. I guess we can restrict the attendance to only UWaterloo people. Yeah, I could potentially. I'll think about it. Yeah, probably I will. Thank you for asking. Okay, now let me now again show you the. Let's click on this one. I want you to see this form as well. So let me go there. Okay, so here is the anonymous feedback form. This is going to be open throughout the semester. I'm not going to close it. I will do my best to check it at least once a week to see if you have any concerns. So it could also be anything that you like about the course. I actually think it's good to put those things that you like about the course here, because maybe somebody else doesn't like it, and then they come in and say, oh, we don't like this, and I don't have any other pointer that other people's like it. I might actually get rid of it and then change that method that you actually like. So there is no limit on how many feedback you can give me. So anytime you have any feedback, you don't even need to have both positive and negative. Anytime you have any feedback come in, it's going to be anonymous. I won't know who has written those feedback. So definitely use this. This is a great great resource. Am I showing it? Okay. No, I'm not. Okay. Here. Here is the form. I think now I'm showing it. Yep. So here is the form. You put things that you like and things that you think that need to be improved. Okay. Enough of that. Back to the slides. Sorry about all these going back and forth between. Okay, now let's get going. Readings. This is your main textbook. Somebody has already asked on Piazza if it is mandatory to have the books. It's really not. I can't force you to have the textbook, but I really recommend buying it. Either the paper version of it or the Kindle version, which is available on Amazon.com. I think each there are 4 not chapters, but 4 different sections of the book, each one for $8 US. I would strongly recommend buying this book. So one thing to definitely note is that this course, if not the most important course that you would take in computer engineering, it's going to be one of the top 3 most important courses that you're going to take. And this textbook will be a reference for you throughout your career. So this is a great investment, in my opinion, to have in your toolbox. There are 2 other references that you can use. One is Operating Systems 3 Easy Pieces. This is actually freely available online from Wisconsin. And then the other one is the famous Operating System Concepts book that I think is from Yale. So the prerequisite for this course is ECE 252. I'm going to be assuming that you guys know all about the following topics. I'm not going to cover them. I'm going to be partially using them. So if you need definitely refresh your memory, go back to your notes and make sure that you know them all. So I'm assuming that you know file systems, you know what processes and threads are, what is PCB, what is TCB, how can you fork, what is exec, what are the signals, and then what is inter-process communication. I'm going to be assuming that you know all about networking and sockets and ports and client-server programs. I'm going to also be assuming that you know all about concurrency. This is very important. If you need, definitely refresh your memory on this. And eventually, I'm going to assume that you know about deadlocks. basically how to prevent them, how to avoid them, how to recover the system if it happens, and all of that. Okay, so we're going to talk about key systems abstractions that has emerged over time. This is going to be the theme of this course. We're going to talk about the trade-offs between the designs of these system abstractions. We're going to talk about efficient implementation of it. And the thing about it is that you're going to learn how to efficiently use them. So when you know about them, you basically use them in a good way. So here is why you should take ECE 350. Because maybe some of you end up designing a real-time operating system or parts of it, or just an operating system, not necessarily a real-time one. Many of you are going to create systems using the concepts that you're going to learn from ECE 350. And almost all of you are going to write programs that would use the abstractions that operating system provides. So you're going to definitely use them better if you know them. How do we evaluate your performance in this course? So the lab project is going to be the main focus of the evaluation. It's going to have 70% of your evaluation. There are 5 deliverables, and we'll talk about them in more details. You're going to have quizzes, probably 10 to 20, and that would cover 30% of the evaluation. They're going to be online on Learn. They are open source, open book, in a sense that you can use your textbook, you can use the course website, any material that is posted on the course website, but you cannot use anything other than that. So your book, your notes, the lectures, anything on the website, any material on the website, but that's it. You're not allowed to, for instance, Google a question or go to Stack Overflow or any other site. You're also not allowed to talk to others, your group mates, your other people in the class, other people outside the class, even your parents. Don't talk to them during the exam. Anyway, so nobody, don't talk to anyone while you're taking the quiz. We're going to give you 4 days to complete each quiz. The moment you start the quiz, you're going to get 2 hours to complete it. This should be enough because we're designing each quiz to last about 30 minutes. So giving you 2 hours is more than enough. Okay, so one important disclaimer here. We reserve all the right to change these weights at any time during the term without prior notice. And I'm sorry to have this here, but it's a new reality. Unfortunately, things could happen that would change entirely how we, deliver a class. So hopefully this never changes, but just be ready that it might change. And what that means is take every single one of these deliverables seriously. Think about them. Oh, this is my final. So if you do well on each one of them, then you're going to do well on this course. Don't count on these weights. Don't say, oh, this doesn't have enough weight, so I'm going to just take it not taking it seriously, and then eventually you see, oh my God, the weight went up, and you would face problems. So take them all seriously. Hopefully nothing changes, but I'm just putting it there so that everybody is on the same page. Now let's start talking about the lab project, important stuff. Okay, so you're going to be designing and implementing a real-time operating system, real-time kernel. We call it RTX, we call it real-time executive. And you're going to use a board that you can see in this picture, not that guy, the board. So let's talk about serious stuff. First of all, about your groups. Groups should have 4 members. The deadline for telling us about your groups is this coming Monday at 8:30 a.m. I think Irene has already sent you all the instructions on that. We're not going to allow 5. 3 you need to justify. We already, I think, have 1 group of 3, so there would be another group of 3, but that would be it. So we can have 2 groups of 3, but then everybody else has to be 4. Each group has to have a project manager. I'm going to talk about why this is important. I'm going to talk about sort of the responsibilities of a project manager. But just send an email to Irene once your group is announced and tell us who is the project manager. You can rotate this task between yourselves, but the each deliverable has to have 1 project manager. Don't change it in the middle of 1 deliverable. So if somebody is project manager now, he or she should remain project manager until the end of the deliverable, unless something extraordinary happens. But then you can change it. This is very important. And so not only tell us about your groups and the members, but also tell us who is the project manager. You're only allowed to split up your group once. Everybody involved in that split up will suffer 1 day, 1 grace day. So work your hardest to find the best people that you can work with. And everybody only can have only 1 split up. We're not going to allow more than that. These are the milestones for the project. We're going to have 6 milestones, the first one coming Monday. Then P1, P2, P3, P4, P5. You can see the weights, you can see the deadlines. The deadlines also, again, I'm repeating myself. You can find them on the course website, on the schedule. Again, another disclaimer here, we reserve rights to change these weights. So take each one of them seriously. For questions, so if you have any questions, just post it on Q&A. Check the time. Okay. Now, how do we grade you? Well, this picture tells the story. It's really true in most cases. You have, unfortunately, in many cases, we have an uneven distribution of contributions. We want to prevent this. How do we prevent it? We're going to let you guys do peer reviewing for us. So every deliverable, after you submit, you're going to also submit a rating of your teammates with some comments. So the exact format will be determined, but you're going to give us some feedback and then rate your groupmate, all your teammates. Then we're going to just average all the ratings for each member of the group. If your average is more than 8, so the rating that you're going to receive from your teammates is going to be between 0 and 10. And so if the average is above 8, you get all the points for your group. So your deliverable will be evaluated. You get a score, let's say 98. Now, if your rating is more than 8, your grade for that deliverable will be exactly your group's deliverable. Here's the formula. If your average rating is between 7 to 8, you're going to get only 80% of your group's grade. And this goes all the way down to 0. So if from your teammates' perspective, your rating is below 4, you're not going to get any points for that deliverable. This is very important. So please, everybody, be on the same page. At the end, you're going to evaluate each other. Make sure that everybody knows what they're doing and everybody else knows what everybody else is doing, so that you can do a fair judgment of each other's contributions. Now, you might not like your rating. You can tell us if you feel uncomfortable with the rating you receive. In that case, we're going to ask either your TAs or the lab instructor, or at the end, me, myself, we're going to sit and listen to everyone and make a decision. So at that point, we're going to make the decision on how this, how much contribution each person in that group has had. I haven't decided to penalize this, so you can potentially not, tell us that you don't like your rating, but hopefully this doesn't happen. If everybody is on the same page, then hopefully you're going to be comfortable with the rating that you receive from your teammates. Okay. Yeah, start early, please. This is so true that programmers are internal optimists. You ask them, how long do you think the project is going to take? They're going to, oh, it's going to be 2 days. So it's easy. And it's never 2 days. It's not. Start early, start early. I don't know how much emphasis I should put in this. Can you efficiently partition a project? Yes. Definitely you can. I'm going to talk about how you can do that in a moment. It's a general rule that as you get more participants in your group, as your group grows, the workload on each teammate comes down up to some point, but something goes up, and that is communication cost. So you're going to be now communicating with a lot of people, and that has a cost. So at some point, the marginal benefit of getting a new teammate does not justify the marginal cost of communication, so it plateaus. So communication is key and is actually expensive. I'm going to talk about it. Before talking about communication, what are the ways that you can partition? You can partition your group, work in a functional way. So basically, teammate A implements like threads, teammate B implements semaphores, somebody else implements locks, mutexes, whatever. So you do that way. The problem with this one is that you're going to get you're going to face a lot of communication cost, because now each functional unit has to interact with other units. And you need to have clear API, and that requires you to communicate. And then you want to make a change in your unit, it's going to affect a lot of other people's. Unless you keep the API fixed, it's going to impact everybody else. I'm so sorry. So somebody's asking when the lecture will be posted. Okay, so I think I mentioned this. I'm going to say it again. Right after this lecture, the recording of this lecture will be available using the same link that you used to come to the lecture. So the same link to the live session will take you to the recording. Use the same link to watch the video. Hopefully that is clear. Okay, so the other way you can partition your work is by tasks. So you could say, okay, person A designs, person B writes codes, and person C tests. This might be a little bit difficult to do. You have to know, the strengths of each person, but it might be easier to partition this way. It's really up to you which way you pick. You could do a hybrid way, doing tasks and functional, but just know exactly which way you use. I got another question. Okay, so we got a question about when the first lab manual is going to be released. I'm going to let Irene to answer that question. Potentially, probably using the Q&A. You can, let me publish this. We'll get back to you. Irene, if you hear me, you can you weigh in?
Yeah, yes, I can hear you. I'm working on it. I plan to release it this weekend.
Okay, yeah. So before the deadline for
the group
sign up. Yeah.
Yeah. So usually the lab is always released by the deadline of the next lab. So let's say lab 2 will be released by the deadline of lab 1, and lab 3 will be released by the deadline of lab 2. But that's the worst case scenario. Sometimes we get it ready before, right? So we just release it early.
Okay. Thank you.
You're welcome.
Okay. Let's keep going. Communication, very important. Very important. Please know that any change has to be propagated through your group. You have to communicate. Now that you're actually doing peer review, communication is even more important. I got another question. Give me a second. Okay, so I got a question on the deadlines for quizzes. Yes, so we're gonna actually put the deadlines for quizzes on the website. So usually this is going to be the case. The quizzes will be released on Monday, and then you have so Monday right after the class, and then you will have all the way to Friday before the class to complete the quiz. And I'm going to be posting the deadlines for quizzes on the website on the event column. So check the event column for any deadline. Okay. So miscommunication is always something that people usually get hurt. So it actually happens. So deal with it knowing that it happens. Put all your thoughts in your project and definitely focus on communicating. Now, again, you're going to evaluate your teammates, and this is a very important task. You have to be fair. We're talking about their grades, right? So if you communicate clearly with your teammates, if everybody knows expectations of themselves, then things become really easy. Don't let things slide. Don't think that, oh, they should know. No. Tell them whatever you think that they should know. Tell them. Make sure that it's documented. I'll talk about documentation in a bit, but it's really a key. It has to be obvious who is making decisions. So we have the lab. Each group is going to have a project manager. The main job of project manager is to coordinate between everyone. If there is going to be a meeting, it's the job. It's the project manager's job to basically get everybody to participate or set the time. If there is going to be any documentation, it's the project manager's job to make sure that everybody is contributing to that documentation, or he or she themselves have to do that part. If you are going with partitioning your project task-based, so somebody is in charge of the design, then well, everybody should know that that guy is gonna that guy or girl is gonna make decisions on the design. The other one is gonna make decisions on the code. The other one is gonna make decisions on other things. So again, know each person's task, and then who's gonna make decisions based on those tasks or functional units. Coordination. So this is another important thing that I want everybody to be on the same page. We have people on different time zones, and it's really hard to have a meeting that everybody participates. At the end of the semester, at the end of the term, I would expect that many of you are not able to participate in all the meetings that your group has had. So that's a fact. So we're gonna accept it and work around it. So knowing it will help you work around it. Why are we limiting it to 4? Because if you have more, it's even harder to synchronize everyone, put them on the same page. Why we don't let groups less than 3? Because you have to learn to do teamwork. So yeah, I don't exactly know what this comment is, but I'm going to publish it anyways. Okay, so keep going. Now, the other thing to note is that people have different style. Not everybody has the same style. Again, accept this and work around it. Some people work at night. Some people work in the morning. So don't expect everyone to follow your style. Give people room to do whatever style they have, as long as they stick to their responsibilities and deliver those. It should really be fine. Yeah, I'm gonna just move faster. Again, people are human. Your teammates are going to make mistakes. Just take it easy, let it happen, and then work around it. What else do we have? Documentation. Please, please, please document every step on the way. So, you know, give me a second. Yeah, so I'm so sorry. So definitely document every step on the way, document every single decision that you make. Given that maybe someone doesn't attend all the meetings, it's really good to have documentations of the meeting. By default, this should be the job of the project manager, but if you decide somebody else to do it, let that be. The documentation is the key when somebody disputes the rating, and a TA or your lab instructor or myself gets in to make decisions. If we have documentations, if you show us, okay, these are the decisions, these are the documentations that we have, and see this guy hasn't done their part, then it's easy to prove your point. If there's no documentation, then it's your word against that other guy's word. So definitely document in your emails, in like have a shared document. This is very important skill to learn. What are the documents that you should have, in our opinion? Definitely the specifications of your project. You're doing a software engineering project, have the specifications. You know, collect notes on each meeting that you have. Definitely have a schedule documented so that everybody's on the same page. Have an organizational chart, who's responsible for what. These are all the important things, and so much more you can absolutely add. Use software tools. There are so many of them available. There's open source software to do revision control. I guess this is something that you guys should already know, but definitely use the tools that are available to you to make the coding easy. Definitely test your deliverables. Don't wait. So you have a group of 4. Each one of you is going to code by themselves. You're most likely not next to each other. So each person is in a different time zone, different cities, and everybody is working on their codes. And then it's like 30 minutes before the deadline, you want to put all the code together and build and test and submit. That's not gonna work. So at every step on the way, get everybody together, have a meeting, put the codes together, build, and test. Unless you do this, you're gonna face problems. So take it really, really seriously. You're gonna be working on a big project. So if you don't build and test, you're gonna get into a problem and trouble. So I don't know how to emphasize this, but just know. Yeah, you can have different types of tests. You can definitely do it in an automatic way. Write scripts to check and test. Whatever suits you, definitely test. Yeah, test early and then test later and then test again. Everybody's working on their codes. They make a decision to change part of their code, and that could affect your code. So unless you put all the code together and build and test, you won't probably notice it. Late submissions. You've got 5 grace days, including weekends. We're going to count weekends, and including the reading week. So one of the deadlines is right before the reading week. So we're going to count going inside the reading week. And you're going to get 50% per day afterwards. And we're not going to care about 1 hour late or 15 hour late or 20-minute late. Right after the deadline, any minute after that is going to count 1 day. Okay, I have 2 questions here. I guess Irene, somebody's asking about the skeleton code for the project.
Yeah, it's going to be released by this weekend. I've already the skeleton code is already on GitHub.
Okay, yeah. And then somebody's asking about test daemons and testing real-time system. Let it start. You'll see. That's what I would say. Definitely, you're coding, you're writing your system. We're going to give you simulators, so you don't really need to deploy it on the board. That would be possible. I mean, Irene is going to weigh in after me, but you're going to have a simulator. So if you want to test your code, you can definitely use your simulators to test. Do you want to add anything else, Irene?
Yes, we have a simulator, and we also can access the real board. So the simulator is about 1 order of magnitude slower than the real time, but the real board is just a real time.
Okay. Yep. Here we go. So I wanted actually to mention, you're not gonna just hear from me. You're gonna probably hear from my 2 kids, also Irene's kid, probably.
Sorry about that.
No problem at all. I mean, it's new reality, so get ready. You have more than 2 instructors. Okay. After 3 days, there will be no late submission, so you're going to get 0. Collaboration policy. This is very important. You can explain concepts to someone from a different group. You can discuss algorithms with them, testing strategies with them. You can help them debug their code. This is important. You can actually sit with someone, debug their code. That's fine. You can search online for generic algorithms like hash tables, for instance, if you ever need it, or linked lists, whatever that you might want to know. Like generic algorithm, you can definitely search. Now, what is not accepted is, first of all, once your code is done, you cannot share it with others. You cannot share code or test cases with any other group. You cannot open source your code. You cannot post it on your website, on GitHub, on any other website. So your code remains closed source with you. No, you cannot publish your code, even after you pass the course. So let's say you finish ECE 350, you move on, you still cannot post your code. You would face academic integrity problems, and if we find out someone from previous terms has published their code, we reserve rights to pursue that through the university. You cannot copy or read other people's code or test cases, and you can actually not copy or read online codes from prior years from other groups. That's also not permissible. We have 0 tolerance policy for plagiarism. We're going to use MOS, and we will follow university's policy 71 for any single incident. I'm going to actually let Irene talk about lab facilities. Can you weigh in, Irene?
Oh, yes. The lab facilities, we don't have scheduled lab sessions, and everything is basically, you can treat it as an open lab. There will be tentative demos to evaluate P3, P4, and P5, but we, again, disclaimer here, well, we might change. Let's say if we see there's a need to evaluate P1 or P2 by the demo, we will do that as well. But for now, the plan is to do the demos for P3, P4, and P5. And to access the lab facilities, you go through the EngLab. There's a website called englab.uwaterloo.ca. You have to be on VPN in order to access those computers. Then you select ECE, ECE-RTOS. There are 27 machines there. They are all Windows 10 machines, and then you pick one of them. I believe there's a policy, so if you're idle for a certain number of minutes, say 20 or 30 minutes, then you're going to automatically get kicked out by the administrator, and your account is locked for that computer for a certain period of time. How long, I don't know, but I've been kicked out myself for a couple of times when I was inactive. So each computer is a Windows 10 machine, and on that computer we connect a board. This board is what we call Kyle MCB 7000 LPC 7068 board. It's a microcontroller, and on the Windows 10 machine we have MDK ARM, the light version, which is free. You can also download it and install it on your own home computer. So this is the main IDE we're going to use. By using this IDE, you can either run your code under the simulator, or you can also run it on the actual board. And once I release the Lab 1 manual and the corresponding like video clips, then you will have a better understanding how the things work. So just so as you know, the simulator may not perfectly match the hardware behavior, but it's a very useful tool. Actually, 85% of the development you will do can be done by the simulator. But what does that mean? That basically means, you know, once you finish your coding, test your code on the hardware. Okay, especially starting in P3 when we have the serial port interrupt stuff, it's very important for you to test it on the hardware, because the simulator will initialize certain things and make your code working under the simulator. But if your code doesn't really do that initialization, you try to do it on the hardware doesn't respond. So the code that only works on the simulator will lose 15% of the project mark. So we need the code to be able to run on the actual hardware. And actually, that's the most important and most interesting part of this project. We're not doing under a simulated virtual environment. We're doing it on the real hardware.
Thank you. I usually give people 5 minutes, not 5 minutes, 3 minutes of break. But because so far I haven't been talking about really course material, so I'm gonna skip it this time. From the next lecture, we're gonna have breaks as we go. I got a question. Does NGLab work on Mac? Irene, do you want to weigh in?
I'm muted. Okay, yeah. I was muted. I was talking. Anyway, for Mac users, unfortunately, they don't officially support it. But I saw my TA who used the crossover platform, and then they installed this Kyle IDE. With this crossover, it works, but I believe crossover is not a free tool. I don't know how much it cost. So in last term, when we had lockdown, all the Mac users, they just access the tools through the NGLab. It's something equivalent as NGLab. It's so remotely access these tools.
Okay. Thank you.
You're welcome.
Okay, so let's move on. You can definitely seek help. Use Piazza, email us. We have office hours, so use our office hours. If that doesn't work for you, if you have a class on that particular time, shoot us an email. We can definitely find a way to meet you and set up an appointment. So your important near-term task is basically sign up for a group and then wait for the first lab manual to be released. Finally, before I get to the lecture today, work hard, but then relax harder. I know for sure how stressful and hard it is for every single one of you, for myself, for everyone. These are really unprecedented times, hard. One thing to note is that we are aware of the difficulties you're going through. There have been multiple surveys. Students have voiced concerns about their workload going up. We understand that. One thing to note is that we haven't added extra work to this course. So everything that you see here is not because of the course being offered online. The only thing that is because of that is the quizzes, which would substitute the exam. But then we're also accommodating you by giving you extra time and making them open book. I got another question. Yeah, so I'm gonna let Irene answer this question on the Q&A. Just answering it with text. That would I want to move on and get started with the. Thank you so much. So okay, now let's get rid of my. Okay, so let's get started. For the remaining time I have, I think I've got about 25 minutes. So what is an operating system? Well, there is no universal accepted definition. One thing that you could think of is, sorry, I got another one. This also Irene is going to answer on Q&A. Okay, so what is an operating system? Well, you could say whatever is shipped when you order an operating system. Let's say you get your Mac. Whatever is shipped with it is kind of an operating system. It's a good approximation. If you buy a Windows machine, it's going to be that. If you go and download Ubuntu image, that's sort of going to be a good approximation of what an operating system is. One thing that is universal, everybody agrees, is that one program that is running all the time on your computer is kernel. And every other piece is going to be an application program. For the purpose of this course, we're going to define an operating system as a special layer of software that sits between the hardware and applications. And its job is to provide an abstraction view of the hardware. It's going to hide the complexities that the hardware has and comes with hardware. It's going to provide a very clean interface to the applications. And the other important task of operating system is to protect applications from each other and protect itself from the applications. On a side, the operating system is going to also provide facilities for security, authentication, communication, and such. So here is to just put it all together. The first task of an operating system is to be an illusionist, to provide a clean and easy to use abstraction of the physical resources. So let's look at it in details. Let's focus on the interface of hardware and software. What do you have? So in your software realm, you have your running program. In your hardware realm, you have a processor that is connected to the memory. And then processor has a bunch of registers. Floating point registers, for instance, integer registers, program counter, stack pointer, all those registers. And it's going to get the value for those registers from the memory of that running program. On the way, to make things a little bit faster, it's going to cache some of those information because you don't want to all the time go to the memory and come back. You want to speed it up, you cache it. The other thing that happens on this way between the processor and the memory that we will talk about in details is page tables and TLBs. I'll go into details of what these are, but they also sit there. You also have a storage. You also have other devices, your mouse, your display, your networks. all of them are connected to the link between the processor and the memory, that the bus over there, through a controller. Each one of those devices has its own controller, and then the entire bus probably has its controller, and all of them are connected to each other. The hardware provides instruction set architecture interface. This is an interface. The hardware tells the software that these are the things that you need to know about what I'm providing. So this would be instruction set architecture. You've already seen some of these in ECE 22, and a bunch of you who actually has taken ECE 320 are going to see more of this actually. What is then OS? OS is going to sit on top of all of this. So this is what you just saw, and we're not going to just let the application to see this bare metal hardware. We're going to put a layer that we're going to call operating system. Operating system looks at the hardware and uses the ISA to communicate, and then provides abstraction. So instead of showing them all the details of the processor, we provide an abstraction called threads for our processes. Instead of memory, we provide address spaces. For storage, we provide files. For our network, we provide sockets. You probably have seen many of these already in ECE 252. And then sits on top of this another abstraction, which is called process. Again, you've seen it. This is just reminding you. So the process sits on top of operating system. It's just an abstraction that operating system provides and looks at those resources through these abstractions. And then you, as a programmer, you have your compiled program. You use system libraries, and you just launch a process to use all those hardware. So that's the first job of an operating system as an illusionist. The second job of operating system is a referee. So operating system is going to act as a referee. It's going to provide protection and isolation and sharing of the resources. So let's see. Here I have exact same figure, but then I have two processes. The things that are important to us now, when the processor is running process 1, the registers inside the processor are getting updates from the memory that is associated with that process. Now, if I want to switch between processes, switch from process 1 to process 2, well, I got a question. So the question is, when we're talking about operating systems, are we really talking about kernel? Yes. So kernel basically implements operating system. Kernel is that one program that implements operating system. But we're going to actually see things that. Let me get back to this question in more details. So we're going to see some other things that operating systems might provide through libraries, not necessarily through kernel. So operating system is basically, if you want, is the management of your this abstraction layer. Most of the things are implemented inside the kernel, but operating systems usually also provide system libraries, like libc, for instance. Is provided by the operating system to the programmers, and it's not inside the kernel. So they're a little bit different. When we're talking about operating system, we're talking about that abstraction layer. Most of it implemented inside kernel. I hope that answers the questions. Okay, now let's say we want to switch from process 1 to process 2. What do we do? Well, the first thing we're going to do, I'm so sorry. Okay. So the first thing to note is that each one of these processes has its own address space, has its own memory allocated inside the memory. So now we want to switch between the two. What we're going to do is we want the processor registers to have their values updated from the memory of process 2. Well, that's how we do it. We just now make sure that everything inside the register file, the registers of the processor, come from the memory of this guy. What does it mean to provide protection? Well, it means that if the process wants to access memory of process 2 wants to access memory of process 1, or it wants to access the operating system's memory, or it wants to have an unlimited access to the storage without any protection, the operating system is going to show up and say, no, you're not allowed to do this. The guy is going to get a segmentation fault. We'll talk about this in more details. So this is the job of the operating system, to weigh in and as a referee and protect itself and other processes from any process. The protection layer, the protection boundary, if you wish, is something along these lines. So basically, we want to protect the operating system's memory and all the hardware from the processes. And the only things that they could, in a restricted way, access is going to be the processor and their memory. So, yeah, we talked about these. The third job of an operating system is to be like a glue, provide common services to the applications. This is where things get a little bit gray in terms of what is really operating system and kernel. Well, here's where you're going to see this. So your operating system is going to provide I/O. The processes want to access the display, the network, and all of that. So the way for them to access to the I/O is by providing them a way to bring data from those devices to the memory where the process has access. And this is basically commonly provided through I/O. For instance, in Unix, every communication you have with I/O happens through files, and that's the service that operating system is providing uniformly for all processes. So the other thing that operating systems provide that might not necessarily be implemented inside kernel is the look and feel. How do you feel? Like, for instance, how it feels to work in Linux is different from Mac, is different from Windows, and usually it's provided by the Windows service. And again, usually it's part of the operating system. It's debatable if it is operating system that has to provide this or if it is software, but it's a general. I would argue that because we're actually dealing with the hardware, we're dealing with the display, and we're providing an abstraction, so it's basically the operating system, and it doesn't really matter who is implementing it. Is it kernel? Is it system libraries? That shouldn't matter. This is the job probably of the operating system. The other thing is background management, things that we not necessarily see. For instance, you have a battery that has to be managed. You want to shut the system down when it's not used, or save battery in some cases. These are also the tasks that operating systems have to deal with that would not necessarily being shown to the end user. The bottom line of the operating system is to support applications and to basically be transparent, not show yourself to application. Be as minimal as possible, as the least amount of overhead as possible. Let the applications run efficiently on the hardware with the least amount of overhead. We're going to rely on the hardware to provide these abstractions. So we're going to use hardware supported instructions that are only provided to the operating system to provide this illusion, to provide protection, to provide to act like a glue. We're going to rely on hardware. We'll see basically what that means exactly. We're going to rely on dual mode operation. We're going to rely on interrupts, traps, exceptions, memory management units. These are the supports that the hardware provides and the operating system uses. The reality is actually operating system design continues to evolve. And the reason for that is because hardwares are evolving. Hardware devices are evolving, and application requirements are also changing over time. We'll see more of that later. So to just put it all together, what do operating systems do? Well, they provide an abstraction through file system, processes, threads, virtual memory, naming systems. They also manage devices, and they do this by implementing a bunch of algorithms and mechanisms that would be the focus of this course. We're going to talk about scheduling. We're going to talk about how we can implement concurrency, how can we implement transactions, security. So as you can see, this picture on the right, you have a very narrow operating system in between, and then wide area for your software and wide area for your hardware. You can have a lot of complexity, a lot of types when it comes to your applications, when it comes to the hardware, but you don't want to change the operating system every time your hardware changes. So you want, by creating abstractions, you want to just have a stable operating system that can deal with changing applications and changing hardware. So how do we do this? Well, we convert what the hardware gives us to what the application wants. So this is basically our job. See what the hardware has and provides and what the user wants. To do this, we need to ask two questions. What is the hardware interface and what is the application interface? We're going to call the hardware interface as the physical reality, and we're going to call the application interface as a virtual machine. I got a quick question. So what do I mean by operating system is incidental? It means that it has to have minimum footprint in the system. You should not be the important part of the system. You should be invisible, basically. Just get in when it's required and then get out and let the applications run. Because if the operating system is consuming all the resources, let me first publish this. This was a good question. So if you are if the operating system has a lot of overhead, that means that most of the time the operating system is using the processor, the resources, then there is not much left for the applications to use. So you want to be incidental. You don't want to be the main focus. You want to just get there when it's required and get out and manage the system that way. Okay, so what is this virtual machine that we just saw? We need to provide this abstraction of virtual machines. So basically, this is what we talked about. It's the illusion that your applications own all the entire machine for themselves. they shouldn't be seeing each other. They shouldn't be seeing operating system. It should feel like they're running on bare metal hardware, whatever the hardware is providing. There are two types of virtual machines. So one is process virtual machine and one is system virtual machine. Let's see, how much time do I have? I've got 7 minutes left. So what is process virtual machine? This basically is what operating system does, right? As an operating system, you just run one process, and I mean, you run a lot of processes, but for each process you run it and you provide that illusion that that process owns the entire hardware. You also have things like Java virtual machine that would also run a Java application and provide exact same abstraction layer, or JavaScript, or your probably your browser. When it runs an application, it's kind of like providing that process virtual machine. The other one that is more involved is called system virtual machine. That would sort of support execution of entire operating system. For instance, VMware, Fusion, VirtualBox, Parallels desktops, then these are the examples. Let's dive into each one of these. So process virtual machine, basically each program, each process thinks they owns the device. They think that they have all the memory, the CPU time is all for them, and they can use it as they wish. Now, you want to provide isolation. You want to protect processes from each other and from and protect yourself as an operating system or the virtual machine provider from the processes. Java is basically a good example. If you don't want to just focus on operating systems, you can actually look at Java virtual machine. That's basically a process virtual machine. A more involved way of providing virtualization so somebody's asking what's the difference between process virtual machine and system virtual machine. So the main difference is what are they providing abstraction to. So in process virtual machine, you're providing abstraction to one process. In system virtual machine, you're providing abstraction to an operating system. So when you have something like VirtualBox, you can install Linux on your Windows. You can install Windows on your Linux. So that operating system thinks that it has all the resources for itself, and that operating system can launch any number of processes. So it's basically who we are providing the abstraction to that would distinguish between system virtual machine and process virtual machine. Now, if you focus on system virtual machine, you have two types. Type 1, so before getting there, so the system virtual machine, as I mentioned, you're going to provide an abstraction that would allow an entire operating system to run and think that it has all the resources for itself. Now, you want to basically manage all your virtual machines, all these OSs, all these operating systems that are running. How do we do that? We have an entity that is going to provide and manage these virtual machines. We call that hypervisors. So we have two types of hypervisors, type 1 and type 2. What's the difference exactly? Well, type 1 hypervisors, they allocate hardware resources to their virtual machines in addition to managing them. So there are two things to focus on. One is allocating resources, hardware resources that are available. Second, managing virtual machines. Now, like who runs now, who runs next, how to protect them from each other, how to provide isolation between them. So type 1 does both of them. And an example of it is basically VMware, ESXi, and Xen. Type 2 basically just does the virtual machine management and relies on a host operating system to allocate resources. I got a question. What sort of virtual machines are processor emulations? such as QEMU. So QEMU is basically a system virtual machine, because then you can actually install an operating system on your QEMU. So let me publish this. So it would be a system virtual machine. Okay. There is a third and a new way of virtualization that is a basically low weight alternative to full system virtualization. It's called containers. So they're a little bit different from full system operating systems. They're not going to provide abstraction to an operating system. They usually provide abstraction to processes or to virtual machines, but they rely on the kernel, so they don't bring up an entire operating system. But they provide a lot of abstraction to so if we are talking about, for instance, something like Docker, you provide abstraction between all the applications that you're running. How much time do I have? So 1 minute. So I got a bunch of questions. So I'm going to answer these questions actually in next lecture, and we'll just resume from this slide. Let me see how many slides I have left. Yeah, I've got a couple of more slides to go. So I'm gonna end the lecture here. Hopefully I'll answer the questions that I have here today. I'm gonna publish them, but then I'll answer them in the next lecture. If you have any other questions, definitely shoot me an email. I think with that, I'm gonna end this lecture. Take care, be safe, and see you on Monday. Bye-bye.